Properties of inclusion, an overview. In precalculus, you might have encountered the concept of a monotonic function. Monotonic means increasing or decreasing, and it could be strictly increasing or weakly increasing. For instance, the linear function y equals 1/2 x. This is a function whose graph is a straight line, and it starts low in the coordinate system, and as we move to the right, the point on the line goes up. That's a monotonic function, more exactly an increasing function. We are going to consider monotonicity of the union operation, intersection operation, and the difference operation. So the question is, what happens with the union if I look at the union of x1 and y1, and if I make x1 bigger, if I take a superset x2 of x1, and similarly with y1 I'm replacing it with a superset y2. So when I'm saying bigger, I'm using this word in an intuitive way, just taking a superset. So now point 1 says that if x1 is a subset of x2, if y1 is a subset of y2, then when I have the union of x1 and y1, the value of this union will be the subset of x2 union y2. The union operation is monotonic or increasing in this sense. Similarly, for the intersection, when I replace x1 and y1 by supersets, the result of the operation is a subset of the new expression. And finally, I'm going to consider the difference, and I'm taking the difference of x1 and y1, and then I want this to be a subset of x2 minus y2. In this case, I need to make x1 bigger, but with y1 I need to be careful. Y1 actually needs to become smaller in order to achieve such an effect. We're going to prove point 1 of this fact, and in order to do that, we need to recall some basic properties. X is a subset of y if and only if, for every element u. If u is a member of x, it is also an element of y. And u is a member of the union of x and y if and only if it is a member of x or it is a member of y. So now here's the point 1 of this fact again, and we are starting a proof. Please notice that the statement in question is an implication, if, then. In order to form a direct proof of an implication, we assume the antecedent, and the consequent will become our goal. In the next step, we will look at the form of the goal. The goal is an inclusion. Using the definition of the inclusion, we can say for every u, if u is a member of the left-hand side, it is also a member of the right-hand side. And our new goal is now, we have maybe I should say, we have an additional assumption that U is a member of the left-hand side. And our new goal is that U is a member of the right-hand side on this line. The new goal replaces the previous goal. And now let's take a look at this assumption. U is a member of X1 union Y1. We know that this means that U is a member of X1 or a member of Y1. So we will split the proof into two cases. These cases cover all the possibilities. Whatever U we consider, it must be covered under case 1 or under case 2. The cases are not disjoint. There might be elements U which are described under both cases. But whenever we split the proof into cases, we do not insist on disjointness of the cases. The only important requirement is that the cases cover all the possibilities. So now let us continue with case 1. This is an additional assumption the case gives us. We still work under this assumption, and this is our goal. So in case 1, I can say that using the assumption marked by an asterisk, or more exactly using this part of this assumption, I can see that U is a member of X2. And this brings me really close to the goal. If U is a member of X2, then it is also a member of the union involving X2. And we have reached our goal, this goal. Case 2 is similar to case 1. I'm asking you to write completely case 2, and this will complete the proof of the statement in question. Now some exercises. For practice, repeat the proof above on your own. Make sure to write case 2 in full. After that, attempt a new proof. The statement we proved concerned monotonicity of the union operation. I'm asking you now to consider a similar statement but involving an intersection. And finally, let's consider again monotonicity of the union. We proved the monotonicity in a form similar to this, but using just inclusion, not the proper inclusion. And interestingly, it turns out that replacing inclusion by proper inclusion doesn't result in a correct statement. So now I'm asking you to disprove that this statement holds. For this, you need to find particular sets x1, x2, y1, y2, which make the antecedent true, but also such that the consequent of this implication becomes false. If you're still working on these exercises, please pause the video. Here's another set of exercises. Please make diagrams, think about the statements in question, and answer if they are true or false. I would like to offer a comment about the importance of the statements which are listed here. They contain some very essential algebraic properties of the union operation, the intersection operation, and the subset relation. Later in the course, we will talk about orders and partial orders. It turns out that the subset relation is an example of partial order. And in some way, we could think that x being a subset of y means that x is smaller than or equal to y. And with this understanding, the union operation becomes the least upper bound of two sets, the smallest set that contains both. The intersection gives us the greatest lower bound. And now points 1 and 2 tell how to characterize inclusion in terms of the union or in terms of the intersection. Points 3 and 4 are concerned with the fact that x is always smaller than x union y, and similarly for y, or that x intersection y is always smaller than x. I'm using the word smaller in an intuitive sense. And finally, the statement that establishes x union y as the least upper bound and x intersection y as the greatest lower bound. Let's look at 5. If both x and y are subsets of z, then also x union y is a subset of z. All these things will be discussed in detail later, and I'm not asking you to analyze these interpretations at this point. It is more of a side remark. However, even without considering such concepts, you should be able to answer whether the statement 1 through 6 here are true or false.